All right, well, good morning, everybody. Thank you for joining Flex Train, a flexible training opportunity brought to you by Johnstone Supply. So today we're celebrating a very, very big milestone. So yesterday we hit 1,000 subscribers on the YouTube channel. And what that means is, we've reached out to now 5,000, like 200 hours of watch time on the channel. So we're affecting both technicians locally and abroad. We have people here in our own region, my own technicians. We've expanded out and started bringing in more people into our platform. Paul's from Illinois. I see all kinds of people from Illinois popping on the YouTube channel. I just had a guy just last week from Eastern Illinois University send me a great big thank you. So he went back and he had watched our Lock and Learn series on EPA prep and just wanted to send a thank you and an appreciation for what we've been doing. He watched all of our videos, studied online, and passed his universal EPA on the first try. Huge deal. That's what we're really here for. We're here to just make a difference in the technicians that we work with on a daily basis. So, when we started doing the YouTube channel, it was really just an archive for the classes that we've been doing, just so we had a place to put them. So if we had a technician go, hey, you have any additional information on, say, static pressure? We go, yeah, I got a little 30-minute video, and all of a sudden it just went boom. And we've even had like almost 20 hours of viewing from Guam, and it's like, okay, that's really interesting that there's people around the world, Turkey and Canada and Germany, that are watching our videos and going, wow, these guys are really helping bring HVAC into just a common perspective. And that's really been the goal and the mission of this from day one, is just to take these things that may feel a little complicated, may feel a little overwhelming, and just help them make sense. And we see it every day, and our tech support calls have just been boom, that excited. That was 100 year
It dropped about like that, did huh?
Yeah. Oh my gosh, I'll have to come back to that later. Edit. All right, I'm gonna pause just for a second. Okay. I've been that excited because it just shows the impact that we've had. I mean, if we think about that, so in the last little over a year, we've done, I think we've got 124 videos now on YouTube, over 5,000 hours of watch time, and we're starting to get people going, hey, this really is helpful. This is making a difference. So, we're going to keep on continuing. I've already got the calendar out through the end of the year. And, we're just wanting to continue this education and bringing some of our vendors in and some of our OEM manufacturers along the way, which we've done quite a bit. So I just thank everyone for joining us, participating, and man, it's been a good year, and it's going to continue being a good year. So let's talk about static pressure just a little bit, right? So, as we're talking about fall coming in, right, we're going to be in furnace season. We're going to be back moving our routine from AC into heating. And, the one thing that we encounter on a daily basis that is still a struggle, even with advanced technicians, is understanding static pressure and understanding how static pressure affects our entire operating system, and how, as we are moving into more advanced pieces of equipment and more advanced filtration systems, it is just overwhelming our static pressure on our duct system. So let's talk about duct design just a little bit and how we're checking static pressure. We're going to use a manometer. I wish GoTo could bring in my manometer, because I absolutely love that. So I'll actually have that edited for the YouTube video. So we use a manometer to see what kind of pressure we have on our duct system. So the big misconception in the industry is we'll have technicians, I'll ask for, hey, what's your static pressure on the system so I can help understand what's going on? And they'll go, hey, yeah, I checked my return and I checked my supply, and this is what my number is. I go, well, let's talk about where you're checking it, because a lot of people are just not properly taught where to check static pressure. So if we think about that number, that magic number, that 0.5 inch, half inch of static of water column, that is a number that is coming from the manufacturer of the equipment for the blower specifications. So that number is, it's being designed into that piece of equipment so that it can operate in its parameter based on external pressures. So anything other than what the manufacturer constructed. So if we think about a gas furnace, there's a lot of other things besides that ductwork that's interfering with our static pressure. Every time that we take our static pressure, it needs to be isolated to our piece of equipment. So we're going to take a reading between, let me grab my Sharpie here. Everybody knows I like my handy dandy Sharpie. We need to, because the manufacturer doesn't know what kind of filter we're going to be putting on this system. They have no clue whatsoever. So they want you to add your filter into your measurements. So our filter is going to be part of our return side. It is not going to be included in our measurement on the back side. It is going to be included with our return. So we have to take a measurement between the filter and the blower. And I have guys all the time go, well, hey, I put my filter rack right up against my blower. There's no place to do it. And it's like, you got a whole blower cabinet. That is your return that is between your filter and your blower. That's the cavity that we're looking for. So I've been trying to help installers understand that it's very important to put some inspection ports on your equipment as you're installing it. So we want to have one between our filter and our actual blower. And then on the outlet side of our furnace, remember, if it's a high efficiency furnace, that secondary heat exchanger is a major restriction on our system, but it has been calculated into that furnace. So we need a measurement that is between the furnace and the coil. They recommend that you have a riser between your furnace and your coil, but we all know that that's not going to happen out in the field. We're going to set a cased coil right on top of a furnace. So we either need to make an inspection port that has basically two plugs, one in the face of the coil, the door, and then one in the inspection cover of the coil inside of it. It takes a little bit of work to get that set up and typically needs to be done at installation. Or we can find us a location on the side of the furnace that is in the air path and not in the heat exchanger. We've got to be careful not to drill a hole in that heat exchanger. That's why I say installers need to be doing this, because they're the one can look inside and go, okay, here's where my tubes are. I need to stay away from these. I do have a lot of guys that will take out the main limit and actually check static pressure from the main limit. And that is fine, as long as we're in that airstream, as long as it is after the secondary heat exchanger. That's the downfall. We just have to make sure we know our location. So when we're talking about this, we're going to have a negative pressure that is going to be on our return side and a positive pressure that is going to be on our supply side, but it is the pressure, the actual restriction that is happening and the static that is happening on our ductwork. So we're going to have a negative number on the return, positive number on the supply, but we're going to add those together. So if I had like a 0.2 on my return, a negative 0.2, and a positive 0.3 on my supply, I'm going to have a 0.5. And that's where the manufacturers would like for us to be, is around 0.5. So when I was designing HVAC systems, I always built my duct work around, so I built my total duct system for a total static of around 0.1. And if I do my return, it'd be around 0.08, because I knew at some point I'm going to have a dirty filter. I'm going to have restrictions on my return side. It's just inevitable. Sometimes on my supply. So that gets us in the ballpark, but then we have all of these other external factors, and I want to talk about those and how those are starting to change now that we're moving into higher efficiency equipment, but that also means sometimes more restricted equipment. So just remember, on a gas furnace, we are isolating the furnace. Everything else is external to that furnace. If we're talking about an air handler comes from the factory with a coil in it, right? Either an A coil or a slab coil. Long time ago, they used to send some filters in air handlers from the manufacturers, basic fiberglass filters. If it came from the factory with a filter in the filter rack, that filter came from the manufacturer as calculated as part of that system. We don't do that anymore because of that same factor. 20 years ago, we typically really only had two filters. We had a hog hair and we had a standard fiberglass. And that was about it. We didn't get into too much pleated stuff. Well, now we have all these different manufacturers of filters, and most of them are really not acceptable for our systems. And I'll talk about that here in a second. So we now have our coil and our blower and our heat pack that is going to be part of our system, and that is going to be calculated from a manufacturer. So for an air handler, we have to simply go between the filter and the coil, because our coil is going to be the inlet of the air handler now instead of the outlet side on a gas furnace. Our coil is before our blower. So we have to take a measurement between our filter and our coil, and then we're going to take a measurement between our blower and our supply plug. And that is going to be our external static on an air handler. If we think about a package unit, a package unit comes from the factory typically with filters already installed in it, right? It's going to have a rack system that sits in front of the evaporator coil. And so we are going to have a complete package unit with filters. So that 0.5 is already calculated from the manufacturer to include those standard filters that comes with the unit. If we upgrade filters past that point, then we're going to have additional static on our system. But we can look at our ductwork and take measurements directly from the return, directly from the supply, and that'll be our external static on a package unit because it came from the factory with a coil, blower, and filter. One that we're starting to see that people are getting really hung up on when you're matching equipment is modular blower package systems. So if we're talking about an air handler, remember that air handler came from the factory with a coil in its cabinet. It was calculated with an evaporator coil. Modular blowers, those are paired to a cased coil, right? That modular blower did not include that cased coil. So when we do static pressure on a modular blower and cased coil combination, which is a common replacement for an air handler, if you call a supply house and they don't have your air handler in stock, they might go, hey, I don't have that air handler, but I got a modular blower that we can put a coil on there. What coil? Whatever one fits, right? There could be a whole selection of coils. So the manufacturer says, we don't know what coil is going on our modular blower, so we're going to give you the specifics for our modular blower. Here's where things can start getting really, really tricky. A lot of the new coils have a lot of restriction to them, and people don't realize that, how much that has changed over time. Because, as installation issues, we are trying to fit our pieces of equipment in a replacement height, right? Well, if you all remember, when we started going to high efficiency gas furnaces, they increased their height because we added that secondary heat exchanger, right? So to compensate for that, a lot of manufacturers had to shorten their coils to try to fit into a same space. The downfall of shortening coils is that we're going to have to put our fins closer. We're going to have to start coming up with new shapes besides A's. We may have to come up with N or M coils to try to fit the same amount of slab space and surface space in a short distance. Well, what happens anytime we cram things together? It's going to make things more restrictive to airflow. So when we're looking at equipment, we have to understand the things that affect our airflow, both from the coil perspective, the filter perspective, and how our entire duct system is designed. Because if we look at how airflow is distributed through an entire duct system, we have a lot of places that already have restriction on them, right? If we look at a duct layout, when I designed my supply at 0.1 and my return at 0.08, that was just for my trunk work. That's not including registers. That's not including return filter grills. That's not including elbows. That's not including dampers. There's a lot of additional resistance that we're putting onto our system. That's really what static is. A static is a calculation of the amount of resistance that we have on our system. So we have a variety of places that we're going to meet resistance. And now that we're getting to more efficient equipment, we're going to start meeting a lot more resistance, which means we're going to have to do some duct work calculating to make sure our equipment is going to be functional. When we start getting into some of these like Dyke and Fit that we talk about all the time, fantastic pieces of equipment. They use a variable speed blower motor like many manufacturers are going to. And the thing that we hear the most from guys is, oh, those variable speed blowers will overcome static pressure. And that's a load. It does not. There's always consequences to static pressure. And what we find with variable speed motors is this additional static, this additional pressure. Where's it all going? It's going into our blower assembly. That's where the pressure is actually being felt. So if our blower is feeling this additional restriction, it's going to use more power. It's going to produce more heat. And so the consequence of poor ductwork on a variable speed, we've talked about this so many times, is that we are now going to try to maintain RPMs, or we're going to try to maintain CFM, depending on which motor you have. And to do that, we're going to either increase torque or increase RPMs. And by doing so, we increase power consumption, and we increase current, and we increase heat. So understanding this static pressure is so important. If we look at the additional pressure that is being applied on our blower just based on the filter alone, this particular diagram, so this was taken from an evaluation of OEM filters dropped into systems that already had adequate pressure. So we're talking about a pressure drop of around 492 feet per minute, which is an average residential AC duct system. So that equivalent would be like a 16 by 25 filter running at 1367 CFM. Okay, so we got a 2-ton heat pump with a 16 by 25 filter. It's pretty common install. It could be 1-inch filter, it could be a 3, 4, it could be whatever size it is. So some of these filters have different thicknesses to them, but they're all being set on a 16 by 25 principle. So if we look at the static drop, when I used to design duct systems, I typically used around a 0.13 to 1.5 for a filter, and I typically used a 0.13 and 1 or 1.5 for my coil, because back when I did this 15, 20 years ago, 0.13 was very acceptable for a pressure drop on a coil. That was common. That was back in the 10 SEER days, right? So there wasn't a lot of restriction across the coil. The coil hadn't, consumed more heat transfer space. Well, if we look at what filters are doing today, this is an independent study, right? If we look at what we're doing now, yes, we can still go buy that disposable filter that is around a MERV 2, and that's going to be in that 0.1 to 0.5 range. But as we increase that MERV rating, it's not always an exact correlation between pressure drop and MERV rating. A lot of that has to do with the material that that manufacturer is constructing it of. But if we look at some of the pressure drops that are happening on our systems, you notice that some of these, look at this MERV 8 pleated filter that is doing a 0.6 static, 0.6 on a MERV 8 filter. My manufacturer only wants 0.5 across the blower. I have already exceeded my nominal rating for my blower with only a filter. That doesn't include my supply duct, that doesn't include my return trunk, that doesn't include any additional accessories I put in, UV, humidifier, registers, grills, nothing. 0.6 with my filter alone. And I will tell you that with these variable speed blower motors, we're finding that between 0.8 and 0.9, they start locking out on internal overload, internal temperature overload. So any system, any variable speed system, as we approach 0.8, and especially by the time we hit 0.9, you are going to have equipment problems and equipment failures. It's going to try to protect itself from overloading and from heat. So understanding what that filter is doing to your total system is going to be more important than it ever has. And you can find this information. All you have to do is go to the manufacturer's data plate or onto their website, and they will show you and tell you the actual performance of that. If they don't have anything, I will guarantee that there's companies out there that have already aftermarket tested that. So we want to take a look at what our pieces are adding to our total system. If we look at coils and how much it has changed on coils, remember, I used to factor around a 0.13 to a 0.15 on my coil, no more than a 0.2. 0.2 would be for a 5-ton unit that was a short coil. Now that we're moving into these higher efficient pieces of equipment, we have to be able to transfer heat easy, right? The only way we can do that is adding more heat transfer surfaces to our coils. So we are now putting our fin spacing much narrower than we used to because we're trying to put more heat transfer plates on our evaporator coil. In that process, we're now adding a lot more restriction than we've ever seen. And this is where it comes into play, particularly if we're doing that modular blower coil and we want to see how much restriction that thing is. It's very much going to be based on the actual coil. So, on this particular one, this has taken us up into 2.5 and 3-ton coils. If we look at the difference on these things, if my equipment matchup says, okay, let's take a CAP, let's use CAP. Oh, there's a CAPEA. There's a great one. So there's a take and fit style coil, 2.5 ton, rated at 2.5 ton, particularly from manufacturers. That's a 2 to 2.5 ton range. So if I was running at 2 ton with this coil, my matchup showed 2 ton on my outdoor unit, and it matched me to a 3026 by chance. That's great. I only have a 0.108 static drop across that. That's not too shabby. That's well within what I would have originally designed it. What if this happened to be matched up to a larger system? What if it was matched onto a 3-ton? Because we'll see that with some of these matchups. We'll see a lower size unit, an indoor coil matched up to a inverter outdoor unit. This could very easily be matched to a 3-ton unit. If as a 3-ton unit, I'm at 0.208. If it happens to be a heat pump, I'm now at like 0.24 almost. That's a pretty significant change, right? If I was designing my duct system to originally had a 0.15 static pressure and I moved into a 3-ton unit, well, I've already moved another 1/10 of an inch. If I put one of these higher MER filters on there, I'm out of range just with my coil and my filter alone. We've never had to deal with static pressure on appliances the way we do now. In the past, it was always fairly well predetermined. We knew an average static drop on a furnace, an average static drop on a coil, and an average static drop on a filter. Those do not apply anymore. We have reached way beyond those capabilities with some of these matchups. If I move into some of these larger coils, because it's real common to oversize a coil, and that's great on airflow, sometimes it's a matter of width. If we look at the pressure drop differences just on widths of cabinet, it makes sense, doesn't it? If I can make my cabinet wider, that gives me more space to put my coil. So it allows me to open up the fins, because if I have a narrow coil, my air has to come through at a fairly sharp angle. If I can widen my cabinet, I lower the angle of my coil slabs and allows my air to flow through easier. So it would change the flow. So if I look at only the width difference, so let's look at a CA, like a CAPF 3636, this whole block right here. This is a 3-ton coil, right? Depending on the width of this coil, because I can get it in 4 different widths, depending on the width of that coil will affect that static significantly. So let's look at, so it's a 3-ton application. I got a 3-ton outdoor unit, so I'm going to be pushing around 1200 CFM. If I am on a coil, that's my narrowest width, I have a factory pressure drop of 0.45 inches. I'm almost to my total limit with my coil only. If I could get that in a D cabinet, it's half of that. It's 0.22 inches. So understanding that the width of your cabinet is going to make a significant difference on the amount of airflow that is capable of flowing through that coil, it's going to help us calculate our ductwork properly. We went out on job site inspections before and went to a piece of equipment that we're getting error codes, like blower fault codes on, and went and looked at the equipment and went, wow, that's a 3-ton with a C cabinet. Why did you go with the C cabinet? Could you went with a D? Well, we took out this 21-inch furnace, so we were putting a 21 back in. Like, okay, that's fine, but have you seen how much it affected your airflow? Because it did affect your airflow a little bit. And they go, well, no, we didn't really look at that. I said, well, if you look at that coil, that same coil, if it was dry, doesn't really have much of a difference. That same 3-ton coil dry is only around 0.220, and the C cabinet width is around 0.220. But look what happens when I add a little bit of moisture onto that coil. Because remember, if I'm going to add moisture onto a coil, I'm going to add some restriction to it. So as that unit starts running, I'm going to be able to move from 0.230 to 0.90. 290. So that's a pretty good jump, simply by allowing that coil to get wet. It can't wring the water off as well. It's a steeper pitch and has more restriction across it. So knowing the total restriction is going to change the way you look at your system. Jesse and I went out on one this last week. We had a brand new installation on an inverter unit, and they couldn't figure out what was going on with it. They were looking at it, they thought they had everything right, and we went and took a look at it. And Jesse, what was our external static pressure on that thing?
1.1
on an inverter system. The old permanent split capacitor system ran. It probably burnt motors up every few years, but it ran. It did just fine. That new inverter, it would go, yeah, I'm going to get up to about 75%, and I'm starting to pull some amps, so I'm not going to go any higher than this. And since I'm going to just sit here around 75% at a 1.10 static, I think I'll just overheat myself and shut down. And it was a brand new piece of equipment that was protecting itself from running hot. It was protecting itself from the poor ductwork. So we literally go measure the capacity of it, go, yep, hey, you got a 36,000 BTU unit on this 70-degree days producing 34,000 and some change BTUs. Equipment's good, back to your ductwork. So unfortunately, we're having more frustrations because of static pressure because our equipment is starting to see the static pressure. We've even got manufacturers out there that are using back EMF off the blower motor to calculate static pressure, and you can look at it in the thermostat because it's that big of a deal. So understand that 0.5 inches total is what the manufacturers want us at. If you've got a variable speed blower that is 0.8 to 0.9, you're going to start tripping out on blower faults. You are going to have callbacks, and you're going to have a very disappointed homeowner because these inverter units are not cheap. If you're going to spend, the money on an inverter, you're going to probably be somewhere between $10,000 and $15,000 for a good inverter system. And you're going to be getting callbacks from that homeowner going, wait a minute, I just spent a lot of money on a system that is not working properly, and my old turd ran great for 15, 20 years. And you go, yeah, that is true. It did. And now we got to look at our problems, because what happens if you put in that MERV 2 or 3 filter? So here's actual static pressure drops on these pieces of equipment. If you go do that installation and you put a MERV 2 or 3 filter and it is rated at around 0.10 inches, which is pretty common, and they take that out and they go buy a brand new, MERV 15 filter, and they don't tell you, I've added 0.30 inches of static to my system just by changing the filter. If I left at a 0.7, they pull the filter out and they put in that real nice, fancy, very well advertised 3M filter, you're going to get fault codes. The blower is not going to accept it. So being aware of how static pressure affects our equipment is really what we need to do. We need to be able to have these kind of numbers. When that homeowner calls and says, hey, my brand new system is not working right, and you verified static when you left, and you verified that you had an operating system when you left, sometimes you can over the phone go, hey, I see that it's been 30 days since we did that installation. Have you replaced your filter recently? And they go, yeah, just did it a couple days ago. And you, oh, okay. What kind of filter did you use? Oh, I used the best one that I could find at Lowe's. And you go, okay, so I need to do a little bit of number calculations with you and show you why those really are not the best thing for your application. If you want to use that, we can change your ductwork so that it will accept that filter, but those filters are really only designed for unusual applications. 99% of our equipment that we work on are not designed to be able to handle a 0.40 inch static drop on a filter. They're just not. We never did. If we designed our ductwork to run with a 0.40 filter, we're going to have twice as much material and twice as much cost on the installation. So be aware of the effects of static pressure and how much that static is going to affect your system. Because in the same way, we have registers that are causing the same issues. I go out and I do me a new installation, and I get a call in a few months because they did a remodel and all of a sudden the system is not running properly. Maybe we need to take a look and see if they pulled out our good, easy flowing registers and they put in those nice, clean oak registers. I will tell you, those registers are the worst thing you will ever do to your system. I didn't put this in a presentation because I wanted to take you all to the site and actually show you. If you go to any of the manufacturers of registers and grills and supplies, they have performance data for them. So let's look at some of them. True Air is probably my favorite. It really is very high quality stuff. We can talk about Hart and Cooley as well. They have the same information. You always have submittals and performance data. So all you have to do is go to the website, pull up their performance data, and they will actually have a true static drop rating for that piece of equipment, for that whatever that piece is. So round ceiling diffuser. If I want to know how much static pressure drop I have on a round diffuser, I can actually pull up my data and I can look at my static pressure drops on those. It's very easy. The thing that you will find with most of these manufacturers, there are some that they do not have performance data for. And I would love to do some questioning about this, but I'm pretty sure I know what the answer is. So if I look at like a 168, that is a solid oak. Let me back out of there and let's look at a 168. 168. Let's see what type of performance data we have for that. Let's just take, those are common ones. We see those at the hardware stores. And, oh, product downloads. That's where it normally is. That's where our performance data is in product downloads. I'll be darned. There is none. I could go back to a standard metal and let's look at standard flow registers. So 154, that's a good one. So let's look at a 154. 154. Let's grab that one. And product downloads. It's either product downloads, sometimes in specifications. Yeah, there we go. Look at there. Performance data. So you'll find performance data on almost all, except for the custom ones. Because as manufacturers, they probably do not want to make these custom aftermarket registers. They're probably forced to because there's a market for it. There's a demand, so they have to make a supply. I would love to see some actual performance ratings on those registers, but you won't find them. They're so bad, they're not even there. So understand the effects of changing things in our system, changing filters, changing registers, changing coils sometimes. Because just because we're taking out a 3-ton coil and putting in another 3-ton coil, that doesn't mean that it has the same static pressure that our original had. So it's important to know that as we increase efficiency, sometimes a consequence is additional static pressure, which will affect our motors. So that's about everything that I had. I really appreciate everybody joining us today. I think I better go inspect my 100-year-old lamp here and make sure I didn't tear anything up too bad on it. And I'll get back and recut some of this video and have it back for us later. And does anyone have any questions or comments on static pressure while we're here? All right, well, everyone, happy 1000th, and hopefully we'll see you with another number up there in a few months. Well, that is kind of the magic number on YouTube. 1,000 subscribers, 5,000 hours of video, and they start watching, going, this person's got something of interest, and we do. So in a short period of time, we've helped educate a lot of people, and I really appreciate everyone joining us. So Paul, Jesse, thank you guys so much, and we will see you all next week on FlexTrain.
Take care.